Hello my dear students of class 12. Today we will be continuing with the second chapter, that is solution, and today we will be discussing about solubility of gases in liquids. Okay, so the solubility of gases in liquids is governed by Henry's law. So Henry's law is for solubility of gases in liquids. So this law tells us that the mass of gas dissolved per unit volume of the solvent is directly proportional to the pressure applied. Okay, to the pressure of the gas in equilibrium with the solution at a given temperature. So it means to say us that mass of the gas dissolved is directly proportional to the pressure of the gas in equilibrium. Okay, in equilibrium with the solution at a given temperature. So N is for the mass of the gas. Mass of the gas which is dissolved. Now this depends upon what? The pressure of the gas at equilibrium at a given temperature. Now this law can also be applied whenever you have many gases which are dissolved in the solution. Now in such cases, the total, now suppose you have say gas A, B, C, then all of them will contribute to this subpressure. Now the total pressure of the gas will be equal to total pressure of the all gases will be equal to pressure of A plus pressure of B plus pressure of C. Okay. Now this individual, now PA is what? Is the pressure of A only, therefore it is known as what? Partial pressure of A. So now whenever you have many gases dissolved in a solution, in a liquid, then the total pressure will be equal to the partial pressure of each component, and the partial pressure here can be calculated by using Henry's law. So please listen to it. Now when many gases are dissolved, then Henry's law can be applied. The mass of each gas dissolved is directly proportional to the partial pressure. So how much gas is dissolved in that particular solvent will depend upon the partial pressure of each gas. Okay, so it is telling us that the mass of gas dissolved will be the mass of that particular gas will be dissolved. The mass of that particular gas dissolved will be directly proportional to the pressure. How much pressure that particular gas is applied at that particular equilibrium temperature. Equilibrium state in the given temperature. Now suppose, to make it more clear, let's take more fraction. Suppose you have, say X2 is the mole fraction of the gas in the solvent and P2 is its partial vapor pressure. So now we are discussing about mole fraction. We are trying to convert this partial pressure. Okay. Now if X2, in our previous video we have discussed about mole fraction. If X2 is the mole fraction of the gas, if X2 is the mole fraction of the gas in the solvent, and P2 is the partial pressure of the gas, then from this Henry's law we can say that X2 is directly proportional to P2. Yes or no? X2 is directly proportional to P2 because the partial, how much gas is being dissolved, can be calculated from its mole fraction, and this gas dissolved is directly proportional to the partial pressure. Okay, so now X2 will be equal to, say, K dash P2. Now here K dash is the proportionality constant. Now if you want to make P2 as your subject, then you will be having P2 will be equal to 1 by K1 dash X2. Now this 1 by K1, 1 by K dash is substituted with K dash. So P2 will be equal to KH X2. Now this KH is what? Henry's law constant. Next what? Henry's law constant. So eventually the mass of the gas dissolved can be calculated in terms of what? Mole fraction. Now that is directly proportional to the pressure, partial pressure of that particular gas. So this you have to keep in your mind. So the pressure of gas over a solution in which the gas is dissolved is proportional to the mole fraction of the gas dissolved in solution. So you can see that the pressure of the gas is directly proportional to what? The mole fraction of that particular gas. So this is Henry's law, and it is for solubility of gases in liquids. Now let's discuss about solutions of liquids in liquids. Solutions in liquid. Solutions of liquids. Okay? Solutions of liquids in liquids. Now, whenever you have solution of liquids in liquids, then you have to remember what is its vapor pressure. Okay? So the vapor pressure, the pressure exerted by the vapor in equilibrium with the liquid at a given temperature is called equilibrium vapor pressure, or simply vapor pressure of that liquid at that temperature. So what is vapor pressure? Vapor pressure is the pressure exerted by the vapor in equilibrium. You have to remember this. The pressure exerted by the vapor in equilibrium with the liquid at a given temperature is called the equilibrium vapor pressure, or simply vapor pressure of that liquid at that temperature. Now, suppose you have two containers. Let's discuss about the first container. And suppose this container is what? It's closed. Now here you have, say, liquid. Now this solvent molecule, only solvent, pure solvent is present. Pure solvent. Okay. Now this solvent molecules will be occupying at the surfaces, not only at the surfaces, everywhere. Yes or no? Now whenever it gets converted into vapor phase, then some of the molecules will be going into the gaseous phases. Yes or no? Now the pressure exerted by these molecules in the vapor phase at equilibrium is known as what? Vapor pressure. Now, since only pure solvent is present, its vapor pressure will be high. Now, suppose you have another container. You have another container of equal volume. This is also closed, and here you have solvent molecules. Now to this solvent molecule, now you have added some non-volatile molecules, non-volatile solute particles. Now this added portion is what? Non-volatile molecules or solutes. Non-volatile means what? It won't be going to the vapor phase. That means if this non-volatile molecule is added to this solution, some of its surfaces will be occupied by this non-volatile solid. Non-volatile, I told you, it doesn't go to the vapor phase. Now what will happen? Now it will stop. Some of the, since it has occupied some of the spaces at the surface, that means the rate of evaporation will decrease or not. Why will it decrease? Because it's not taking itself part in this vaporization, and since it has occupied some of the spaces at the surface, means it's not allowing the solvent molecules to go to the vapor phase. Yes or no? Therefore, now whenever non-volatile solvent is added to this particular solvent, then only few molecules, solvent molecules, will be going to the vapor phase, compared to the one where you have only pure solvent. Here no. Here in the first case, no non-volatile solvent is present, only pure solvent is present. Therefore, more number of molecules will be going to the vapor phase. Therefore, its vapor pressure will be higher. The vapor pressure of this pure solvent will be higher than the solution which contains non-volatile solvent. Okay, so this you have to remember. The vapor pressure of pure solvent is always higher than the solution which contains non-volatile solvent. Okay, now let's discuss about Raoult's law. Now Raoult's law is it is for both binary solution which doesn't contain non-volatile solvent and which contains volatile solvent. So let's discuss this part. Raoult's law. The first one is for binary solution of volatile liquid. For binary solution of volatile liquids. Now this law is also very simple. Okay, so this law tells us, now let's listen to it very carefully. In a solution where you have volatile liquid, okay, volatile means the solution, both of them, they can go to the vapor phase. In a solution, the partial vapor pressure of the volatile component at a given temperature is equal to the product of the mole fraction of that particular component and the vapor pressure of that component in the pure state. So mathematically, what does it mean? It means that partial pressure, suppose you have two liquids A and B, okay, and these two are mixed to make a solution, and both A and B are volatile liquids. Then in such cases, the partial pressure of any one component, say A, will be equal to the mole fraction of A into the pressure of A, the pressure A exerts when it is in the pure state, that is P naught A. This is the pressure whenever you have only A, no B is present. So it has to be multiplied. So the partial pressure of any one particular component will be equal to the mole fraction of this particular component into the pressure it would have applied or exerted, okay, in the pure state. This P naught means pure state. Just remember, similarly for PB it would be XB, mole fraction, it has to be mole fraction again, into the total pressure whenever only B is present. So this is the Raoult's law for binary solution which contains volatile liquids. Now here P naught A and P naught B are the vapor pressure of pure liquids A and B respectively. So this is very simple. Now let's discuss for the other type, for solution containing non-volatile solvent. This is for volatile solid, please don't forget. For binary solution Now Raoult's law for solutions. For solutions containing non-volatile solute. Now whenever we say about non-volatile solute, that means this particular non-volatile component is not contributing in the total vapor pressure. Why? Because we have just discussed, because it's not going to the vapor phase. If it doesn't go to the vapor phase, that means it cannot exert pressure. Okay? It is remaining in the liquid state. Liquid state itself, it hasn't gone to the gaseous state. That means there is no question of what? It exerting the vapor pressure. Please remember this. Now, this part we have already discussed. Since the solution contains non-volatile solute, there is no contribution of the solid to the total vapor pressure of solution. Thus, the total vapor pressure of the solution will be equal to the vapor pressure of solvent in the solution. So, here in this case, since it is non-volatile, it is not contributing to the total vapor pressure. So, the total vapor pressure, dP means vapor pressure of solution, will be equal to the vapor pressure of the solvent. So, the solvent only is contributing to the total vapor pressure of the solution. Now, in such cases, you have to remember this thing. Now, if PA is the vapor pressure of solvent A over a solution containing non-volatile solvent B. Now, if PA is the vapor pressure exerted by, say, solvent A, is the vapor pressure of solvent A over a solution containing non-volatile solute, say B, then what will happen? And XA is the mole fraction of the solvent. Then we have a relation, okay? And X is the mole fraction of the solvent. Then according to Raoult's law, we have discussed about Raoult's law. So according to the Raoult's law, what we have? We have partial pressure of A will be equal to the mole fraction of A into pressure exerted by A whenever it is in the pure state. Yes or no? Now here, partial pressure of A will be equal to the mole fraction of A into pressure of exerted by A whenever it is in the pure state. But here, you know total pressure is equal to the P is equal to the PA. This P is the total pressure, okay? And this PA is the partial pressure. Now, in this case, you have to understand this part. In this case, the non-volatile solute is not contributing to the total vapor pressure. Therefore, the total vapor pressure of solution is because of what? The solvent molecule only. Now, therefore, that means the partial pressure of this A is the solvent. Now, this is equal to the total pressure of this particular solution. Now, therefore, we can substitute this part with P will be equal to XA into P0. P0 A. Okay? So, this part we have to remember this. This total partial pressure is itself equal to the total pressure of the solution. So this is the expression for the solution containing non-volatile solvent. The most important point, once again, the non-volatile part of the component is not contributing to the total vapor pressure. Therefore, the total vapor pressure of the solution is itself the partial pressure of that particular solvent.